Yep.
Welcome. This is our presentation. Our paper's name is a multi-protocol controller deployment in software-defined based IO medical things architecture. Our group name is IoT Arc. My name is Keith Smith. I'm in charge of the OS scripting and part of the ECE department. We have John Morin in charge of hardware security, also associated with the ECE department. Ogchan Ondas with dynamics, controls, system speciality in the mechanical engineering department, and then Kata in charge of VLSI technology, part of the ECE department. And below we have our paper citations. So an overview for our paper. Our paper proposes a software-defined, network-based IoMT, or Internet of Medical Things, architecture. And this architecture would be used in various systems, such as all concerning medical. So that would include hospital field settings, as well as any settings that concern any patient or any sensitive data associating to individuals. So this architecture has various network clusters, such as a WBAN, Wi-Fi, and TDMA. These clusters consist of different communication protocols and a central controller mechanism to manage all incoming and outgoing data. This central controller mechanism also incorporates machine learning-based models to interpret all the raw data. And raw data includes things such as real-time patient statistics, heart rate, anything associated with the medical field, as well as any IoT devices and associated communication protocols will go through this controller mechanism, and then the controller mechanism will determine all incoming and outgoing data based on this paper's architecture.
So for the paper's proposed architecture, here we see our the figure that authors provided in their paper. Essentially, authors with this figure are implying that there are going to be base stations, which would be probably a place like a city or an urban area, where the data is controlled through a software-defined network plane and sent through the hospitals or in different settings of medical care, where they get processed, and throughout the medical care facilities, processed within the capabilities and the medical care would take place. Venkata?
This is the proposed control flow for the SDN-based IOMT. The controller will execute the topology discover operation for the base stations, and it will also detect the workloads of the base station and also performs load balancing in order to increase the real-time performance. And then we move to the ML algorithms, where we can use algorithms if the data has priority. Then we are going to use the time sensitive prioritization. For this, we are going to use the aging technique. So it basically the process of gradually increasing a node's priority related to the waiting time in the queue is aging. In this way, the situation of starvation in low priority nodes can be avoided. It's basically the higher priority node is allowed before allowing the lower priority node to use the network resources. And then if the data doesn't have any priority, then we move to the ML based load balancing. The purpose of load balancing is to distribute the nodes to the base station within the coverage area and making sure that all base stations are used effectively. And if the number of base stations are used are more than in the 5G and 6G technologies, then for such scenarios, this will be implemented on SDN controller so that it can monitor both nodes and base stations and can perform ML based load balancing process. And then it will check with the destination base station defined in the flow table or not. If it's there, then the data will be sent to the base station. Otherwise, it will go back to the controller and repeat the process.
Okay. So now we're going to talk about the strengths that we observed throughout this paper. So the first strength that I think was very valuable with this paper was it provided a very kind of comprehensive view of a lot of different techniques that are currently in the industry, and it also accounted for all of these techniques. So for example, with the network standards, we have 3 different network standards. So we have WBAN, TDMA, and then Wi-Fi or WLAN. And so for each one of these, the model creates a way of interacting with it. And so what that means, practically speaking, is that this is a very flexible system that they developed, because not only can you interface with a Wi-Fi network, now you can interface with a WBAN and a TDMA. And so in real life practicality, you need this level of flexibility, and that is what this was representing for us. In addition, our design was this design of the controller for the machine learning techniques, it incorporated a bunch of different algorithms that are currently very practical. So it had support vector machines. It also had boosted decision trees, k nearest neighbors, and something called the naive Bayes algorithm. And it incorporated all of these into its standard for the machine learning. And one of the common practices of all of these is that they're supervised learning. So it mainly focused on the supervised learning, but in that supervised learning, it had a very expansive network. And so another strength that this paper exhibited was it had a lot of different figures and visuals that you could look at, which made looking through the text, instead of seeing a block of text, you could see, you could actually visualize what the authors meant and how they were trying to talk and discuss about different aspects. So for example, when talking about how they wanted to approach the flow of their model, instead of having to read through 3 paragraphs, you could just look at the flow chart that they showed. And then they also have different pseudocode for their proposed model. And then on top of that, they incorporated for the results, they incorporated a bunch of different graphs so that you could really see how beneficial their model in blue was versus the model in red. And so you can see, for example, delay, the delay was much less. And so they could tell you that the delay was much less, or you could come to your conclusions looking here. And then the same thing when explaining the background for IEEE framework. In order to properly see how the frames and diagrams were functioning in packages, they gave a whole bunch of different examples so that you could really understand where they were coming from. So the final strength that this paper exhibited was the results. And so you can see here, there's a whole bunch of varying results, all of which you can visualize. And you can see, so for example, they have user density. So over here, they have user density without machine learning, and then incorporating with machine learning, you can see that they increase there, and so on. And then, working with delay, packet loss, throughput, bit error rate, and so on. And you can see here, when looking through all of these graphs, you can see a very common trend, which is the blue line in whatever metric we're working with always outperforms all of the other models on the market or common literature. So what you can see from these results now, from the analysis of these results, is that you can find a very strong case that this model is superior to other models on the market, because usually you have some sort of trade-off between error and performance and speed. But in this case, it both improved the error rate and it improved the speed, which is a very strong argument for this paper. You're muted.
Sorry. Thank you, John. Again, moving forward with the weaknesses. The first thing that we would like to outline with this paper's weaknesses is the differentiation between the system we have in our medical care as of today and the comparison to the author's proposed system. So, as we can guess, wireless technology is somewhat more vulnerable to, for example, security attacks, like hackers. Due to the nature of the wireless communication, the signals are sent in a way that so many others can listen. While in wired settings, the bad actors, has to have some kind of connection to the actual wire. So this brings so many questions, but most importantly, one of them is, of course, the efficiency of the costs. So the authors doesn't really address in the paper about how much of a cost that their system will bring to table, and is it more or less expensive than what we currently have today. The other weak side of this paper is the data privacy. Well, as we all know, privacy is a big concern in many aspects of life today. We are having issues for not protecting our privacy. We can lose money or assets. So medical care is also very involved with the data privacy. You wouldn't want anybody to track your heart rate, right? So one of the weaknesses is that they don't really do a deep dive into the concern of privacy. As you can see on the bottom image, I have took a screenshot of the search, the keyword privacy in the whole paper, and I was only able to find one place that where privacy was mentioned, and that was the, unfortunately, citation part. The authors didn't even mention privacy in their introduction or abstract. So just like privacy, there are issues with legal sides of the medical care as well, of course. Since this involves human lives, there has to be a legal basis to apply the system. And due to the nature of the paper, I suppose, because it's written by engineers, there are some things that should have been brought briefly, maybe, but haven't really got into the paper. So one of the things, John also mentioned it on the strengths. They do a good analysis on the delay portion of the system, like the delay goes down as their machine learning system advances, but they don't really talk about the latency, which is different than delay. So the one thing that comes to my mind is like a surgical operation within a hospital, or maybe there's a surgeon that is operating in a distance, like in another city or a state. The delay is, of course, important, but what we would be more concerned is the latency, because in a surgery setting, we would be concerned with the whole data package instead of the transmission between the hospitals. So yeah, this is one of the legal issues that would be concerning, but they haven't mentioned. The other thing is, every country or every region in the world have different perspectives on legal sides, and since we live in the United States, I was expecting I was expecting to have some kind of information that may have included the US, but unfortunately, there wasn't any real world examples actually. So yeah, again, they kind of started the legal side, like they prioritized the services, but yeah, unfortunately, they didn't provide a good insight. So continuing on with the third weakness, yeah, they apply machine learning, and it seemed to be working good from their simulation. But some of the machine learning results are not very well explained. And one of the examples is listed in this slide. It's the confusion matrix, which represents the true positives, true negatives, false positives, false negatives, which would bring insight to the model's accuracy in terms of detecting an anomaly or detecting the actual disease. But unfortunately, they didn't provide a good insight about this table, and um, I'm able to describe you this table because I'm taking this class right now. I have some knowledge. The only thing that you could gather from the paper about this table is listed on the left side. It's just one sentence that describes this results, which doesn't really describe it, unfortunately. Um, just like this, just like the machine learning figure, um, as I introduced you at the beginning of the presentation, there's an issue with this figure as well. Authors doesn't really specify the area of coverage. So from the simulations, we can understand that simulations are done within these circles because they used 9 nodes, which 8 of them were sensory nodes and one is the controller. Um, but yeah, we see here those 10 nodes or 8 nodes, but overall, we don't really know how big of an area this applies. Is it like a university hospital, like a UF Shands, like a big bunch of buildings surrounded and communicating each other, or is it like a urgent care center where you just go in and there are few more other patients? That's not really clear with the paper. Also, with the simulation setting, um, I have doubts that if machine learning is applicable due to the fact that the sensory output or the sensory input is enough. Was it enough to provide big data in quotation marks for the machine learning model? Yeah, that's the question.
So in conclusion, this paper presents a reasonably compelling argument for a software-defined network-based IOMT architecture. And the architecture proposed in the paper actually provides a flexible, programmable, and manageable structure and proposes a unique model that is then backed by thorough analysis. So as seen in the paper and as discussed previously, there is comprehensive analysis done. The strengths of this paper also include comprehensive coverage of techniques, varied figure variety, thorough result analysis, weaknesses include lack of insights on comparison with today's IoMT, lack of review on legal issues, lack of key figure explanation, and some future work ideas that we had were to implement some theoretical examples into real world scenarios. In the paper, they talk a lot about the theoretical examples, but they don't include it into a real world scenario, such as like a hospital setting. So we'd like to see more of that, as well as incorporating more intense machine learning practices, such as some deep learning traits also done. Thank you for listening to our presentation.